1954, two brand-new jet airliners fell out of the sky. The de Havilland Comet was the future of aviation, the world's first commercial jetliner, faster, smoother, and more elegant than anything before it. Passengers loved it. Airlines couldn't order them fast enough, and then, without warning, two of them disintegrated in mid-air. 35 people died in the first crash, 21 in the second. No distress calls, no engine failures, no bad weather. The aircraft simply broke apart at cruising altitude. The investigation that followed changed aircraft design forever. And the answer came down to something almost no one had considered. The windows were square. Today, every commercial aircraft you board has oval or rounded windows. Not because they look nicer, not because of some design trend, but because square windows nearly killed an entire industry. This is the engineering story behind one of aviation's most important lessons. To understand what happened, you need to understand what an aircraft fuselage actually experiences during flight. At cruising altitude, a commercial jet flies at around 35,000 to 40,000 feet. At that altitude, the outside air pressure is roughly 1/4 of what it is at sea level. If you opened a window up there, you'd lose consciousness in seconds. To keep passengers alive and comfortable, the cabin is pressurized. The air inside is maintained at a pressure equivalent to about 6,000 to 8,000 feet altitude. That's low enough to feel relatively normal, but high enough to reduce the pressure difference between inside and outside. But even with that compromise, the pressure differential is significant. At cruising altitude, the cabin pressure is pushing outward against the fuselage with a force of roughly 8 psi. That doesn't sound like much until you consider the surface area involved. A typical passenger window is about 25 by 35 centimeters. At 8 psi pressure differential, that single window is experiencing an outward force of over 450 kilograms. Every window, constantly. For the entire flight. Now multiply that across hundreds of pressurization cycles over the aircraft's lifetime. Every time the plane climbs and descends, the fuselage expands and contracts. The metal flexes. Stress accumulates. This is called fatigue. And fatigue is what killed the Comet. The de Havilland Comet was revolutionary in many ways. It was the first jet airliner to feature large, square passenger windows. The designers wanted to give passengers a clear, expansive view. Square windows maximized the visible area. They looked modern. They felt luxurious. But the engineers made a critical miscalculation. When you cut a hole in a pressurized cylinder, you create a stress concentration. The material around the hole has to carry the load that the removed material would have carried. Stress flows around the opening like water flowing around a rock in a stream. With a circular or oval hole, that stress distributes relatively evenly around the perimeter. The load spreads out. No single point bears dramatically more stress than another. With a square hole, everything changes. Stress doesn't flow smoothly around corners. It concentrates at the corners. The sharper the corner, the higher the concentration. At a 90-degree corner, the stress can be 2 to 3 times higher than the average stress in the surrounding material. The Comet's square windows had corners. And at those corners, the aluminum skin was experiencing stress levels far beyond what the designers had anticipated. But stress concentration alone doesn't cause immediate failure. The material was strong enough to handle any single pressurization cycle. The problem was repetition. Every flight, the fuselage pressurized and depressurized. Every cycle, the metal at those corners flexed slightly. And every flex created microscopic damage. This is metal fatigue. It's not about the material being weak. It's about cumulative damage from repeated stress cycles. Imagine bending a paperclip back and forth. The first bend doesn't break it. Neither does the second or the 10th. But eventually, after enough cycles, the metal fails. Not because any single bend exceeded its strength, but because each bend created tiny cracks that grew with every repetition. The same thing happened to the Comet. Microscopic cracks formed at the window corners. With each flight, those cracks grew slightly longer. The pilots couldn't see them. The maintenance crews couldn't detect them with the inspection methods of the time. And then, After enough cycles, a crack reached critical length. The pressurized fuselage did the rest. When a crack in a pressurized vessel reaches a certain size, it propagates almost instantaneously. The internal pressure forces the crack open. The stress at the crack tip intensifies. The crack extends further, which increases the stress even more. This is called rapid fracture propagation. Once it starts, it cannot be stopped. In the case of the Comet, the crack likely traveled the length of the fuselage in milliseconds. The aircraft didn't slowly break apart. It exploded outward from the inside. The cabin depressurized violently. The structural loads exceeded anything the airframe could handle. The aircraft disintegrated. 2 aircraft, 56 people. All because of corners on windows. The investigation into the Comet disasters was one of the most thorough in aviation history. The Royal Aircraft Establishment in the UK conducted unprecedented testing. They took an intact Comet fuselage and submerged it in a massive water tank. Then they pressurized and depressurized it repeatedly, simulating thousands of flight cycles in a matter of weeks. The results were definitive. Cracks appeared at the window corners. They grew with each cycle, and eventually, the fuselage failed in exactly the pattern seen in the accidents. The engineers also discovered something else. The original manufacturing process had included punch-riveted holes near the window corners. Punch riveting creates small stress concentrations of its own. Combined with the square window corners, these created initiation points for cracks. The lesson was clear. In a pressurized aircraft, every hole, every corner, every discontinuity in the skin is a potential failure point, and square corners are the worst offenders. So why do oval windows solve the problem? The answer is stress distribution. An oval or rounded rectangle has no sharp corners. The stress that concentrates at a 90-degree corner instead spreads out over a smooth curve. The peak stress is dramatically lower. Instead of 2 to 3 times the average, it might be only 1.1 to 1.5 times. That difference is enormous when you're talking about hundreds of thousands of stress cycles over an aircraft's service life. But there's more to it than just the shape of the glass. If you look closely at an aircraft window, you'll notice it's actually set into a larger oval frame built into the fuselage structure. This frame is reinforced. The aluminum skin around the window is thicker. The load paths are designed to flow smoothly around the opening. Modern aircraft windows also have rounded interior corners even where you can't see them. The cutout in the fuselage skin has smooth curves at every transition. The frame that holds the window pane is designed to distribute pressure loads evenly, and the window itself has multiple layers. The outer pane is structural. It's the one that actually holds cabin pressure. The inner pane is there mostly for thermal insulation and to protect the outer pane from passenger contact. There's even a small hole in the inner pane that allows pressure to equalize between the 2 layers. Every detail is engineered to minimize stress concentration and maximize fatigue life. The Comet disaster didn't just change window design. It transformed how the entire aviation industry thinks about structural integrity. Before the Comet, aircraft were designed primarily for static loads. Engineers calculated the maximum forces an aircraft would experience and designed structures strong enough to handle them with a safety margin. After the Comet, fatigue became a primary design consideration. Engineers now calculate not just whether a structure can handle a load, but how many times it can handle that load before fatigue damage accumulates to dangerous levels. This led to the concept of damage tolerance design. Modern aircraft are designed with the assumption that cracks will form. The structure is engineered so that cracks can be detected during routine inspections before they reach critical length. Multiple load paths ensure that even if one element cracks, others can carry the load until the damage is found and repaired. Inspection intervals are calculated based on crack growth rates. Maintenance schedules are determined by fatigue analysis, not just by component wear. The entire philosophy of aircraft structural engineering changed because of what those square windows revealed. You might wonder if there are any aircraft with non-oval windows today. There are, but they're rare and they're engineered very differently. Some business jets and military aircraft have rectangular or trapezoidal windows, but if you look closely, you'll notice the corners are always radiused. There are no true 90-degree angles. The corner radius might be small, but it's there, and it makes a significant difference in stress concentration. The cockpit windshield is often more angular than cabin windows, but cockpit windshields are much smaller relative to the fuselage diameter, and they're set into heavily reinforced frames. The structural approach is completely different from a row of passenger windows. Some newer aircraft are experimenting with larger windows. The Boeing 787 has notably bigger windows than older aircraft. This was made possible partly by the use of composite materials, which have different fatigue characteristics than aluminum. But even the 787's windows are still oval. The fundamental principle hasn't changed. There's actually an elegant demonstration of stress concentration that anyone can try. Take a piece of paper and cut a small square hole in the middle. Now pull on opposite edges of the paper. The tear will start at one of the square corners. Do the same thing with a circular hole. Pull on the edges. The paper is much harder to tear because there's no corner where stress can concentrate. This simple experiment demonstrates the same principle that brought down the Comet. It's not about the material being different. It's about geometry determining where stress accumulates. The Comet disasters killed 56 people, but the lessons learned from those tragedies have saved countless lives since. Every time you board an aircraft and glance at that oval window, you're looking at the direct result of those accidents. The shape isn't decorative. It's not arbitrary. It's the physical manifestation of a hard-won engineering principle. Stress concentrates at corners. Fatigue grows cracks over time. And in a pressurized aircraft, small design choices can have catastrophic consequences. The aviation industry learned that lesson at tremendous cost, and they made sure it would never be forgotten. So the next time you're on a flight, take a moment to appreciate that simple oval shape. It represents decades of engineering knowledge, purchased with human lives, applied to keep you safe at 40,000 feet. That's not just a window. That's a lesson built into aluminum. Speaking of aircraft structures, there's another feature you've probably noticed but never questioned: that tiny hole at the bottom of your window. It looks like a defect, but it's actually another critical safety feature. I've explained exactly what it does in another video,